Welcome, everyone. This is our first What is Aging webinar, and I'm here with Dr. Jose Cordeiro from Spain and Dr. Ian Hale from the UK. The main topic is to define what is aging. It's a very mysterious thing, but we're starting to narrow down the fundamental drivers of what aging is. Just recently, more hallmarks, more drivers of aging were published, and now we're starting to peel back the mystery on what this process is. I'm going to say a few things, and then I will pass it over to Dr. Ian Hale here. And yeah, really appreciate you guys coming on. So you can see here, Ageless Partners. This is what we are representing, and a little bit of mostly just going to just show pretty much just one slide before I pass it over. The main thing being that aging, from my perspective, is at the center of all major diseases. This is something that is really the driving process of things like Alzheimer's, things like sarcopenia, things like arthritis, and so on. And when I talk about aging, I'm never really talking about developmental aging, so the process that takes an embryo and turns that embryo into eventually a man or a woman. So it's really about the thing that is going wrong in our biology, some mistake, something that is occurring that is the thing that we actually do not want as humans. So I'm gonna pass it over to you, Dr. Ian Hale. Go ahead. I want to get your thoughts. What is aging, and how do we really define this?
Well, aging is essentially a degenerative disease which begins as the period of growth of a human being, or indeed other creatures, ends, which can be for a human anywhere between the ages of 16 and 25. The mean age when the biomarkers of aging start to become apparent to laboratory analysis is normally around 21. Okay, but I would like to do a slight rewind before I continue on that subject. One of the things that we have to get out of people's minds, and the quicker the better, is that aging, and the result of which is death, is a completely natural process and is inevitable for all creatures. We know very well that there are creatures which live on this planet, with whom we share this planet, which do not age and which are, by most definitions, immortal. There's a particular type of jellyfish. Many of the squid and lobster family live to extraordinary ages. The same would apply to tortoises, for example, and indeed applies to lobsters. So that's just 6 out of a large number. So let's be very clear at the beginning that aging is neither inevitable nor part of the overall natural process. And I want that to be very, very clear, as I say. Right, what causes it? Essentially, let us say for humans around the age of 21, the cellular transcription process for cellular replication begins to falter. Well, I'll give a couple of analogies for that one. One's a very old one, and one not so much. I'm afraid you won't be old enough to remember the old Xerox machines. They were a way of producing copies of documents, inked copies. Possibly Dr. Cordeiro does, I don't know. And the first 50 or 100 copies you get out of a Xerox machine will be pin sharp. The next 100, you'll start to see it's a bit grayer, it's a bit fuzzier, it's not so good. The next 100 is pixelated, and the one after that you can't see. The aging process in those 4 stages can be likened to that. Probably, but we must then examine the concept of the genome, which is the composition of our chromosomes and genes throughout the entire body. We have about 10 to 15,000 genes, which is a lot less than everybody thought we would have, but there we go. And as part of the genomic process, we can see that as a form of code, very much like the operating system of a computer, except of course this is a quaternary, a 4-character code, not a binary code of 0 and 1 as you would expect with computing. Now, there's long been a theory that aging is inevitable with humans because we are fitted with a biological clock, sort of a time bomb, if you will, that at a certain age is triggered to go off and to set off this degenerative disease, which we've discussed. All the evidence, frankly, there's never been any evidence to support that. Now there's quite enough evidence to show that that was completely wrong. What we're seeing is a breakdown in the program, a corruption, if you will, of the program. We see this with every computer program. When it's used long enough, it will begin to corrupt. It will pick up FARI, it will pick up, all kinds of bits and bobs, and in the end, it will, ultimately blue screen you, which is kind of a cool analogy, actually.
That makes sense. Let me hop in with a question. So, you were saying about cellular transcription, and I liked, some of your analogies with the copy machine and such. Is there anything in particular about the process, maybe just the process of the cell dividing and that loss of information related to any of the hallmarks? Like, do you think any of those, like what information do you think is sort of most valuable that's being lost, and how is that kind of connected to the hallmarks?
But to answer your question, the fact is that, like the genome, everything is connected. You get a fault in one area, it will affect other areas to a greater or lesser degree. So ultimately, this is a breakdown of a program that we're seeing, and how the rate and the spread of how that program breaks down is dependent upon 2 factors. First of all, genetic factors, the genes that we inherit. Okay. The second, and as Professor George Church points out, with complete accuracy, and the second factor involved, of course, is environmental, which is to say epigenetic factors, things from the outside which affect the working of our genome. And this is the essential thesis, and again, he's completely right, of Dr. David Sinclair. So in order to tackle the problem of aging, what we have to do is to reprogram the genome. Okay, that is the only way we're going to do it. We have to restore it to its original function. Now, you were saying that how does this work? Well, it very much depends on which parts break down. We're both aware of Dr. Bill Andrews' work on telomerase. Telomerase is the chemical at the end of our telomeres. And if you want to think of a telomere as like the buffers on a train, okay? Now, every time we get a cycle of cellular reproduction, we're going back to the copy machine analogy here, with that copying action, the telomeres are worn down and therefore become less effective, and therefore the replicated cells less accurate to the way they were, let us say, when we were 16. Now, telomerase coats that the ends of the telomeres. Think of it as Scotch guarding them, so that does less damage, and this will help to produce more accurate cellular replication for a longer period of time. And this is what Dr. Andrews has worked so much on, of course, with telomerase and with patient zero, Liz Parrish, whom who we all know about, and that is an ongoing experiment with Liz Parrish's patient zero. So which parts? Well, different parts of the body, and again, this is very genomically dependent from current evidence, age at different rates. Some people, for example, grow gray at a much earlier age than other people. I speak from bitter experience. And this is, these are genetic factors which we need to bear in mind, of course.
Absolutely.
So we have to look at this process not as an individual thing, okay, but as a complete picture in itself, a jigsaw. We have to get all the pieces in the right place, otherwise none of it's going to work properly. And that's a very important thing to remember. And these teams looking at it from different ways, this is a very good thing to do, of course, because the more eyes, the better chance of finding the solution. And I've learned a great deal from reading up on all these people and reading their experiments, talking to some of them, knowing some of them. Dr. Cordeiro's book, The Death of Death, of course, is one that everyone should read.
Absolutely. I've heard good things about the book. I ordered it for a few of my friends, my Spanish-speaking friends. So
Yeah.
Let's have Dr. Jose jump in here. I know there's it's always a tricky thing on what aging truly is, and there's so many paths to go about stopping it. What do you think, Jose? What is aging?
Well, it is a pleasure to be with you, Jason, your followers, and also with Dr. Ian Hale to talk about all these interesting issues. We are connecting from different places. I am right now in Madrid. You can see behind me the City Hall of Madrid and the fountain where Real Madrid celebrates every time that Real Madrid wins, which is fairly often as the best football team in the world. Anyway, talking about aging, thank you for mentioning that. I have published a book first in my mother tongue in Spanish with a British co-author, David Good, and then we translated into Portuguese, into French, into Russian. It is coming now in Chinese, Arabic, and German. So I'm very excited. And it in different languages, it has been baptized differently. In Russia, there are 2 different editions. And for those who speak Russian, you will understand that it says, death must die. Death must die is not my original name, which was La muerte de la muerte, or in Portuguese, A morte da morte, or in French, La mort de la mort, or in Chinese, or in Turkish, in Russian, and now coming out in German and other languages. I'm still working for a good English publisher, so I hope that the big market in English, England, the USA, Canada, Australia, and many other countries can read the book after China, which is big, or Spanish, that actually we are over 500 million people. In the book.
Once it's in English, I'd love to read it too.
Yes, of course. Thank you. Yes, I'm looking forward to English edition too. Anyway, in the book, I cover about even what is aging, because there is still a lot of discussions about what is aging, which is good. That means that we are learning, we are discovering things. For example, one of the first scientific theories about aging is that it was caused by oxidation, the oxidation of the cells, the free radicals, etc. Then people were talking also about mitochondria. Then people are talking about many other things like telomeres shortening, etc., etc., etc. So there have been several compilations of ideas, and I will just mention three, which are relatively recent and relatively very comprehensive. The first one was probably Aubrey de Grey's 7 main causes of aging. Aubrey de Grey believes that aging is damage of the cells and the organism, and that we can repair this damage. And he talks about 7 major causes of this damage. He published this at the beginning of this century in 2004, 2005, 2006, and later in his book called Ending Aging. Soon after, Felipe Sierra, who is a biologist from Chile that was working at the National Institute of Aging in the USA, he also came up with several pillars of aging. And more recently, in 2013, there was the most quoted article about aging in history so far, which is called The Hallmarks of Aging. It was published on Cell magazine, and they talk about 9 hallmarks of aging. So the 9 hallmarks of aging are not exactly the same that the 7 causes of aging of Aubrey de Grey or the pillars of aging of Felipe Sierra. But the fact is that this idea is evolving and other new theories are being postulated, like David Sinclair. David Sinclair, who is a biologist who works at Harvard University, and he published a very good book, Lifespan, Why We Age and Why We Don't Have to. A fantastic book, and he covers most of the things he's doing himself. And he says that aging is a loss of information of the cell. This is also a very interesting theory, which obviously has to do with the discovery of the Yamanaka factors. Dr. Shinya Yamanaka, a biologist from Kyoto University, who discovered in 2006 4 genes that basically control aging. And you can turn back those genes and make an old cell young again. This was obviously so incredible that you can actually change a few genes at the cellular level and change the age, the biological age of the cell, that he got the Nobel Prize very quickly in 2012. I actually went to visit him at Kyoto University in 2009 before he got the Nobel Prize. But after he made his discovery, of course, and he's an incredible person. In fact, he will be in Spain in a few weeks. We are going to be giving him an award for his fantastic research and for his discoveries. Anyway, so Shinya Yamanaka really discovered these genes that you can basically change, turn on and off, and probably reprogram the cells. And this is called cellular reprogramming or cell rejuvenation. So indeed, today we know we can change biological age at the cell level. And now people like David Sinclair and many others are working at the organ level. And they did experiments with eyes of mice that were the equivalent of 80 human years. And through gene therapy, using the Yamanaka factors, they changed those old eyes into younger eyes, and the mice could see again. So this is done from cell to organ, and pretty soon, I believe, at the organ level, organism, whole organism. As Dr. Ian Hale also mentioned, we know today that there are organisms that are biologically immortal, like some jellyfish, medusa, hydras. They are considered biologically immortal. But even more interesting, we have cells in our bodies, just cells, not even organs, but a few cells, which are the germ cells, the most important. I would say, and the most fun, because they are the ones for reproduction, that do not age. Our germ cells that you have, that I have, that everybody has, they do not age. They are considered biologically immortal. And also another incredible thing is that we have learned that cancer also discovered how not to age. This is an incredible story with a patient, a person called Henrietta Lacks, who was born in 1920, and she died in 1951 of a huge cervical cancer. This cancer grew really huge, like a big apple. The doctors extracted the cancer and analyzed it. And then the cancer, unfortunately, grew up again in her body, and she eventually died. But the scientists discovered that the tumor didn't age, that the tumor, if it had food and water, to put it that way, in a Petri dish, the tumor keeps on growing and reproducing and growing. Well, actually, that tumor is alive today, alive today. And Henrietta Lacks was born in 1920, so she would be 102 years old now, so her cells would be centenarian cells. But these tumor cells, you know, they are young. They are like teenager cells, having sex all the time, reproducing all the time, because they discovered how not to age. And I find this absolutely incredible and important. First, because even though since 1951, we know that cancer cells discover how not to age, we haven't been able to replicate that system, but we will, because cancer didn't go to university. Cancer didn't even go to school. Cancer doesn't know how to speak or write or read or anything. However, it learned how not to age, how to stop the aging process. And also, it did it free. It didn't cost millions of dollars for cancer to discover how not to age. It discovered it basically for free. And this is really incredible because all cancers, because there are many types of cancers, cancers of different organs, different parts of the body, etc., and different people, of course. What they all have in common is that they stop aging. Cancer has discovered how to stop aging in different organs, in different tissues, in different people. So it should not be that difficult now that we have sequenced the human genome and we are trying to identify the mutations that stop cellular aging. So I believe this is really important. We live in a fantastic time. Now that we have sequenced the human genome, we are very close, not only to cure cancer in the next decade, all cancers, I believe, but also to advance in how to reverse aging, how to stop aging, which is what cancer has done for free.
Very well said. I like your analogy to cancer there. That's cancer didn't go to university. That's true. That's true. It's yeah, no, it's that was good. I think it's a multifaceted issue across many spectrums, and I think the main thing is that aging is reversible and not inevitable. And now we're really narrowing down what can be done. And when we look at the landscape, there's so many companies now all around the world, all targeting different areas of aging, all perceiving it in slightly different ways. And now, not all those companies will succeed, obviously, but I think some of them are going to bring us much, much closer to where we need to be. Touching on the hallmarks a little bit, let me just share really briefly. So just recently, this came out. These new hallmarks have kind of been passed around a little bit, you know, since the main paper came out in 2013. And, you know, I really think that there's more hallmarks even to be discovered that have not yet. But they're being discovered pretty quickly and really being refined. Two of them here, microbiome disturbance and compromised autophagy. I think these are big ones. I'm really big on the microbiome. You know, the fact that we have more of these organisms in the body than cells in the body really tells me there is something there. And if you measure the microbiome of someone who's 80 versus someone who's 20, you're going to notice this substantial difference. But it is interesting, you know, the interrelation between all these hallmarks and cancer, like you were alluding to, Jose. And really, the question is to find that balance with these new therapies, where you're trying to get rid of some hallmark of aging without giving rise to cancer. There's sort of this trade-off, you know, if the, you know, between the cellular mechanisms, basically. Any thoughts on these new hallmarks? Any of them in particular, either of you? Or?
Let me actually comment on that, because I was in a conference just a few days ago in Copenhagen, the ARDD conference, which is Aging Research and Drug Discovery. And one of the authors of the original paper, there are 5 authors to this very famous paper, The Hallmarks of Aging. 3 are actually Spanish, which is very interesting. Dr. Lopez Otin, Manuel Serrano, and Maria Blasco. Those 3 are Spanish, and actually Manuel Serrano has just joined Altos Labs, and he's moving from Spain to Cambridge, where there will be the European Center of Altos Labs. Anyway, the other author that I also know, Linda Partridge, she spoke at this conference in Copenhagen, and she told me they just have submitted a review of their original paper from 2013, talking about the hallmarks of aging at that time and now, and new things that have to be considered. So this is very timely, Jason, what you are showing. And one of the things I also particularly like is inflammation, because our immune system that takes care of many things, obviously, including inflammation, our immune system begins declining at age 20 or about, when we are in our 20s. And this is a tragedy, because then our immune system cannot cope with inflammation and cannot cope with many problems like cancer. And this is quite interesting, because we get cancer since we are born. We continuously get cancer cells, but our immune system is relatively so powerful until we are in our 20s that it destroys the mutant cancer cells. Even though we get cancer all the time, our immune system suppresses it, destroys it. But then the immune system begins declining. Our thymus, which is this gland here, begins disappearing and becoming fat, and we don't have an immunological system that can really protect us against cancer, many viruses, bacteria, parasites, and inflammation. In fact, sometimes this is also called inflammaging, which is the combination of inflammation and aging. Another thing separately, not really in the hallmarks of aging as such, but I really find fascinating, is young blood. Young blood obviously has something which is good, and old blood has something which is not that good. In fact, which might be bad. And we are also very close to be able to analyze almost everything in blood. All the proteins, everything in blood. Once we discover this, hopefully, you know, in a decade, hopefully not much later than that, we will be able to understand what is important about young blood and why this treatment, sometimes called parabiosis, which is changing young blood into old organisms to rejuvenate them. And also the opposite is true, sadly. If you take old blood into a younger organism, it gets older as well. So there is something very interesting, very important about blood that we will discover scientifically. And, you know, blood goes throughout our body continuously. So blood is very, very important, just like the immune system. The immune system monitors the whole body completely. So these, to me, are very systemic causes of aging, or something we need to understand. The immunological system and inflammation related problems, and obviously blood, young blood. So I want a lot of more young blood. So Jason, if you want to do some blood exchange, I am up for it.
I can definitely give some over anytime. Definitely willing to give some of my blood, and then I'll recreate new blood in theory too.
Yes, but let me, okay, I was saying that as a joke because we all know about Dracula and all of that. But my point is that in 10 years, we will be able to create any kind of blood artificially. In fact, we can already create basically artificial plasma, and we will be able to create artificial red cells, artificial platelets, artificial white cells. I think we are very close, and to understand all the proteins and all the other components traveling through our blood. So I don't have to get your blood, Jason. We will do this scientifically.
Yes, no, it's a lot of good points. I mean, so on the blood piece, I definitely agree. I think that to some degree, we're going to go beyond biology, and we're going to be able to create synthetic blood that is better than any natural blood. So that's going to be good. I definitely believe in, unfortunately for the older blood, there is likely some kind of bad factors in there. There's something in the older blood that we can quantify and that we could say this is something we don't want. And I'm sure that there's something in there. And there could be something in young blood as well. There definitely, and there likely is. And I think that it's a huge area of research. I think that it's definitely going to be great, especially the synthetic one, especially when we make blood that's better than anything nature has made. I think that is going to be a major breakthrough, and I think we will get there. Circling back to inflammation, I think this is a big one. This whole concept of the immune system aging, and this phenomena that happens, like that you were describing with apoptosis, essentially, where the body determines which cells to kill, and it's very interrelated to senescent cells. The body has tagged these particular cells to kill themselves using apoptosis. Then that process doesn't happen correctly, and because of that, you get these senescent cells, which is one of the major causes of aging. You can see the sliver here, cellular senescence. So I wonder too, and I'm sure there's companies working on this, if there's just a better tagging system that the body could maybe use, maybe some kind of artificial therapeutic that really tags those cells, those senescent cells, for apoptosis and really triggers that natural mechanism. I don't know if you guys have thoughts on that. I'm sure there's someone looking into it.
Yes, there are a lot of people looking into it. Essentially, what happens is that as the cells die off, you can think of it as like the scaling inside a kettle or inside a pipe, and it's one of the causes of heart attacks, strokes, etc. As the epithelial cells of the blood vessels begin to break down, as you say, because the process is no longer as good as it was, these dead, let's be clear, these dead cells build up layer by layer by layer. They narrow the arteries, the capillaries, they narrow the veins until that causes an event, obviously, which we don't want. And that is a symptom of aging. It's not a cause. That's the first point. Inflammation, which is measured by a CRP test, and which is part of the protocol, Jason, that you and I have described, because as the protocol that I've developed is used, then these biomarkers of aging will change and reduce. So a patient with an initially high CRP, it stands for C-reactive protein test, as the protocol works on them, that level of inflammation as a biomarker will drop. Another important biomarker of aging is bone density, the amount of calcium within the bones. As people get older, they lose calcium, and this leads to osteoporosis, and more fragile bones, which is why so many people, when they get old, they fall, they have a relatively minor fall, they break a hip or a pelvis, and they end up in hospital, of course, having to have a major operation, a hip transplant, or major surgery to repair the pelvis. And often because that means that they're bedridden for a long time, they will contract pneumonia with, obviously, terminal consequences. So, this is something again. So all of these things I said about telomere attrition, how they're worn down with each cycle of cellular replication. The problem is, as you pointed out with telomerase, is that too much telomerase, yeah, it stimulates the production of cells. But problem is that's all cells. If, as Dr. Cordeiro has pointed out, we all contain within us cancer. You put a lot of telomerase in, and it's throwing gasoline onto a fire. So it can trigger cancer. And I know this is an area that Dr. Andrews is looking at very closely, and why his biomed AT65 is formulated very carefully, not to be so strong as it will do, so that it won't, it won't do that. I mean, he's told me that he could make one 100 times stronger, but obviously the risk reward factor is, negative at that stage. So that's what we need to be looking at. Yeah, I mean, there are a lot, all those biomarkers are very important ones. But inflammation is one very important one, and I certainly agree with Dr. Cordeiro there. Cellular senescence, absolutely, and one that was mentioned earlier, oxidative stress levels can be relatively easily can be measured very easily, which is obviously a big plus. So
absolutely.
Let me continue with the telomeres. I think this is a very important subject. So I would just like to add a few things, because I am a very good friend both of Bill Andrews and Liz Parrish, who was patient zero. In fact, I just invited her to Spain 2 months ago. She was here in Spain, and also in a big event, including Barack Obama. We had Liz Parrish, Barack Obama, and myself in a huge event, over 20,000 people, talking about aging. And Liz Parrish talked about her own experience. And what Dr. Ian Hale is saying is obviously very important, because there is a perfect correlation, or very good correlation between the length of the telomeres and the shorter and shorter they get, and the possibility of getting cancer. But even though there is correlation, there is no causation. In fact, the causation is the opposite. If your telomeres are long, then you don't get cancer. And that is what has happened with Liz Parrish. She injected herself the first time with telomerase, which is the enzyme to grow the telomeres, and her telomeres grew. So she actually rejuvenated 20 years, and she did not get cancer. Why? Because her telomeres are long enough so that her cells don't need to mutate and grow telomerase artificially. So actually, there is correlation, yes, but there is no causation. In fact, it's the opposite. If your telomeres are long, you do not get cancer. This is, in fact, one of the things we will cover at the biggest anti-aging conference in the world. I am gladly one of the organizers. It's called RAD Fest, Revolution Against Aging and Death. RAD, Revolution Against Aging and Death. And because I'm Spanish, I always yell, Viva la Revolución! Because it is a revolution. And Liz Parrish will be talking there in October. This is October 6 to 9 in San Diego. Also, Bill Andrews will be there, and many other people, including from different areas, like my friend and former boss, Ray Kurzweil. Ray Kurzweil, who is also basically an immortalist, but he comes from computer science. He doesn't come from medicine or biology, but he also believes that we will reach longevity escape velocity, or demethyl by 2029 to 2030. He will talk about that, longevity escape velocity and demethyl and rejuvenation technologies for everybody, basically for free, at the latest by 2045. All of this you can discover if you come to RAD Fest, Revolution Against Aging and Death. And after that also, I organized a conference in Spain about Plan B. And well, Plan A is not to die. And I think we are very close not to die, because if we make it into the 2030s, we will basically live long enough to live forever, even if aging, until we do rejuvenation technologies. That, again, that should be for everybody by 2045. However, people will still die now. And for those people who die now, we have Plan B. Plan B is cryonics. I also believe in cryonics. Actually, I did the first cryosuspension of a Spanish person in the Iberian Peninsula. Now we have 4 Spanish people in cryonics. And this is moving very fast worldwide, because we truly are between the last mortal generation and the first immortal generation. So it is never good to die, but even less now. It is worse to die now, because we know we are very close to the end of aging, to have indefinite lifespans. That is why I think cryonics will also grow in the next 2 decades for those people who sadly die before we have rejuvenation technologies. So anyway, this is just to invite you to come to Madrid in November 12, 13, and to come to San Diego, California, October 6 to 9, to talk about all the latest of the latest in anti-aging and longevity treatments in the biggest event in the world of its type.
Yes, that's and I'm looking forward to that. I'm going to be there in October. It's going to be amazing. Definitely looking forward to that. Ray Kurzweil has been a good influencer on many people. Definitely looking forward to hearing his talk as well. And obviously cryonics has a big play, and I'm a fan of cryonics as well. And you know, one of the core themes, you know, is for at least for us, for Ageless Partners, is to accelerate our path to this future that Dr. Cordeiro is describing. You know, we have dates, we have them set out, and you know, right now a lot of people are they're in the latter stages of aging, and they don't have cryonics. So there is this sense of urgency that you know, and this call to action that we always ask for everyone to try to push this forward and try to move it forward as quickly as possible, because I feel, or we feel, Ageless Partners, that we have a moral obligation to do that. So thanks, Jose, for those insights there. Very well said. Nice. So this was good. I really appreciate you guys.
Can I make a couple of points? We were talking about young blood. As you know, part of the protocol that I've developed, that we've discussed, is therapeutic plasma exchange, TPE. It's been found that that it is as effective as young blood. The problem with the young blood approach is screening, essentially, as it is with everything, particularly as we still are living in the age of active COVID, and it is a fairly fast mutating virus, and it is absolutely impossible to screen blood for what might be the latest mutation that might be discovered, for example, in 2 to 4 weeks' time. So I would be very, very risk averse to using young blood. But TPE has been found to be as effective, and that stands for Therapeutic Plasma Exchange, as I say, which is basically bloodletting, which obviously reduces blood pressure. High blood pressure is another biomarker for aging, as we well know, because it is partly caused by the narrowing of the veins caused by the dead cells that you discussed. And we've discussed senolytics, which is to say preparations which flush out the dead cells, very much like using, can I advertise here? And I hope this company will pay me for this. There's a product called Rad Flush that you can put into car radiators and household radiators, which removes all the scaling and everything else. Basically, senolytic drugs do that, and they are part of the protocol to reverse aging, to rejuvenate, which you and I hope to bring to the public within 12 months of now.
Absolutely, yes, and that's definitely true. We want to bring this rejuvenation protocol to people to really take an old person and make them young again, pretty much.
Yes.
I've heard numbers. I know like a few foundations, going 90 to 50, 80 to 60, whatever it is. But we do want to measure things clinically. We want to show, that we're able to actually prove that we've reversed aging in all 78 organs and the microbiome. Ideally by 2030. That's the goal. So. Quick
well, I
question.
hope the goal is to do it much earlier than that, and this is why we're interested in biomarkers, as you know.
Absolutely. Yeah, I'm a big fan of age reversal versus longevity, because longevity can't really show. I mean, age reversal, you're going to know right away, does that person, physically look and feel younger. Quick question on you were saying about TPE. This is essentially, just so I understand, this is some form of blood that's being transferred. It's just a particular component of blood.
It's essentially saline.
Oh, saline, or?
Yeah, with some nutrients added.
Okay. So it's filtering out maybe some of the bad.
Yeah, I mean it basically, one of the great things that getting rid of about a liter of blood does. Is of course that as the old blood comes out, which is full of these senescent cells, you're actually getting them out of the body, which, as we said, is a great thing. You're reducing inflammation, therefore you're reducing telomere attrition, and also attacking other things by putting the clean saline in. That adds as Rad Flush. Just remember, guys, I'm advertising you here, and that will also help to take more of the senescent cells and the free radical damage caused by oxidative stress. Essentially, we rust up inside. We have water, we have iron, which is why our blood is red. And of course, what happens when you add water and iron? You get rust. And this is another part of the reason that our blood vessels become clogged. So this solution also acts against that process. So it's a very effective thing to do. And once we have, through the process that we're going to talk about in secret in the near future, I hope, dealt with the genomic problem, then we can deal with the biomedical side once we've dealt with the biophysics.
Absolutely.
And this is what I intend to do.
Yes. I'm very much looking forward to that. I'm going to take us offline here in a second. Any final thoughts, Jose or Dr. Ian?
Well, I agree with all that has been said, and I think we're moving very fast. The changes are not linear, they are exponential. In fact, I like to say that in the next 20 years, we will see more technological advances than in the last 2,000 years, because this is moving fast. And also, Jason, even though you are much younger than me, you are an old man today compared to what I will be in 20 years. In 20 years, I will be younger than you are now, but hopefully you will be younger too.
Thank you. I definitely hope so. It's aging is the biggest killer on the planet. So definitely, I'm glad we can target, we can figure out what the problem is and what aging is. And I hope you're 16 in 20 years, you know.
But by the way, I believe truly, like Ray Kurzweil says, that in 2045, we will have rejuvenation technologies. And then we will remember today how primitive we are today, that we let people age and die. This is barbaric. This is very primitive. But we will have solved that problem by 2045.
Absolutely, I agree. And a lot of people, you know, just a final note, you know, on that, I think a lot of people, they underestimate the rate of technological change. They can't really forecast in a linear way. And, you know, really, it's all centered around AI. I mean, once an AI can truly think, and once an AI can truly be on the level as a human, you know, we can deploy billions, if not trillions, of these entities, and we're going to see progress much, much faster than a lot of people think. It really, that's going to be that inflection moment that really changes the game. So
I think that nanotechnology as well is going to be a very important thing in terms of repairing damaged systems. And yeah, I'm not sure I'd actually want to curse somebody to be 16 again. I think we'll say 21. You know, 16 is kind of a pretty tricky age. I really want to say thank you to you, Jason, for arranging and hosting this, and Dr. Cordeiro, you know, always interesting, and a big thank you to everybody who you know, who watches this. Please share it, and the message I'd like to leave with everybody is that aging and death are not inevitable. They're not an irreversible law of nature, and we're going to prove it.
absolutely, absolutely. Thank you, Dr. Ian Hale, and definitely agree on everything you said, including nanotechnology, which I know we didn't get too deep into, but maybe on the next one, we'll talk about how that will be at the center of our future research. So thanks again, guys, and I will take us offline here.